Okay. Okay, the next talk is by Ralph Jung about higher order ghost state.
Okay, hi. So I'm Ralph, and here's the one-slide version of this talk. I'm going to be talking about Iris, which is a higher order concurrent separation logic that we developed over the previous years, and that we want to apply to verify the safety of Rust. The key technical contribution of this talk is to show how to overcome a limitation in the previous versions of Iris, namely that Iris did not support higher order ghost state. So I dropped a bunch of free variables here. So next thing I'm going to do, obviously, is to explain what that is. Let me start with Rust. Rust is a new programming language that has been released by Mozilla previous year. And it's a language that tries to strike a balance. On the one hand, we have languages like Java, Go, or Haskell that have like high-level, beautiful abstractions that we all came to love and that guarantee safety at the expense of control that we have over memory allocation or scheduling of the program. On the other hand, we have low-level languages like C, C++, or even assembly that do provide all the control we could ever hope for at the expense of safety. So Rust tries to, well, eat the cake and have it too. And to this end, it provides both the high-level features that we like higher-order functions or polymorphism or traits, which are like essentially type classes with associated types. It also provides fine control over when and where things are allocated and how things are laid out in memory. And it tries to keep you safe by having a sophisticated type system that's all built around the idea of ownership, that is, threads having exclusive access to some particular part of the memory. And to make sure things don't become too simple, Rust also has support for concurrency, and it guarantees data race freedom as part of its type system guarantees. So our goal as part of our work in the Rust Belt project is to verify that this is actually true, that Rust and its library are actually safe to use. Now, for this job, we need to pick the right tool. And the kind of tool we're looking for is a program logic, because we're trying to verify properties of programs. Now, what kind of program logic are we looking for? Well, for once, we want a separation logic, because Rust type system, as I said, it's all about ownership. And separation logics, well, really, they could also be called ownership logics. So this is a natural choice. Next, obviously, we want support for concurrency. And finally, we need stuff to be higher order, because Rust is higher order. Now, it turns out that there's a whole bunch of concurrency logic that have been developed over the previous years. Ilya made this beautiful picture, summing most of them up. And it turns out most of them are separation logics, namely all of them that descend from CSL, there in the top right corner. Furthermore, we don't just have many concurrency logics, they also tend to be complicated. So these are some of the fundamental proof rules of some of the modern logics here. And these are like the very foundational proof rules that have to be verified directly in the model that everything else rests on. So in previous work, we explored whether we can't like make something simpler, maybe. So with Iris, we proposed a logic that is built on two key mechanisms, namely invariants, which are pretty much exactly what you think they are, and user-defined ghost state, which I will be explaining now. So let me start by saying what ghost state is. It's also sometimes called logical state or auxiliary state. And some examples of it are auxiliary variables that we add to the program to ease verification, exclusive tokens or capabilities that represent the right of particular threads to perform particular actions, and monotone state, which for example includes trace information that can only grow over time. Most of these prior logics come with support for one form of ghost state or another, but generally the shape of the ghost state was fixed by the logic. The key point with user-defined ghost state is that you can mix and match the pieces of ghost state that you want or need for your verification. And the reason this works fairly neatly is that it turns out that this ghost state actually has a common structure, and that's the structure given by a partial commutative monoid, or PCM. Essentially, a PCM is the minimal algebraic structure something needs to have to be ownable in a separation logic. So it consists of a set M defining the resources which threads can own, like, for example, partial heaps. and a composition operation, which is commutative and associative, which tells us how to combine the ownership of different threads, for example, disjoint union. Now, it turns out that it's not very hard to figure out the PCM structure for these existing examples of ghost state. So what we did with Iris is we made invariants and any PCM for the ghost state the foundations of the logic. And just to convince you that this is actually not so complicated, I'm just briefly popping up the core proof which is governing these mechanisms. And as you can see, they are not so bad. We then went ahead and showed that we can actually derive all these more complicated reasoning principles in the logic. It's not like we don't want these reasoning principles. They generally have been invented for a reason. We just don't want them to be the very foundation that everything else rests on. So this completes the recap of the Iris 1.0 story. It turns out that there is a key limitation here, which is the point of today's talk. Namely, there are some specs for synchronization primitives which we can't actually prove. The nature of this limitation is fairly easily explained. So if we look at how a user will typically use Iris, you start by picking the PCM of your choice, which you want to use for your verification, and then you instantiate Iris with that PCM. Now, what happens if you want your ghost state to talk about the logic? We call this higher order ghost state. We have a ghost state referring to the assertions of the logic. And, well, now we have a circular dependency. And as we all know, this is asking for trouble. And in fact, Iris was not equipped to handle higher order ghost state. So the contribution of this work and this talk is to motivate why higher order ghost state is useful and to demonstrate how we can extend Iris with higher order ghost state without sacrificing this idea of building anything on the everything on the simplest possible foundations. And we also verified all of that stuff in Coq. So let's get started with the motivation. Let's look at a synchronization primitive, namely a barrier, which is the idea is that a bunch of threads, the waiters, can be made to wait until one thread is done computing some job. So for example, here the thread in the middle would be doing some computation, and then the other threads would be waiting until the thread in the middle is done, and only then they would go on computing. Now, to understand how we would specify such a synchronization primitive, let's first simplify slightly to the case where we only have one waiting thread. We have an ordering constraint here, essentially. That's the core of the synchronization mechanism. And the natural way in separation logic to express ordering constraints is via ownership transfer. So, for example, we can think of the left thread as owning the location x after it computed whatever value it wanted to put there. And then ownership of x is moved through the barrier to the other thread, so that the other thread, the waiting thread, can now read x and do whatever it wants with that. Of course, this doesn't just work for plain x. We can do this with any assertion p that's moved through the barrier. And to make sure that this actually works out, we have to guarantee that both threads agree on what is the resource that is sent through the barrier, because otherwise, obviously, mischief could happen. So we have to add some management here. And to understand that, let's look at the specification. So this is how the spec for the barrier would look in separation logic, a bunch of 4 triples. And these things which are added here are capabilities. They represent the exclusive rights of threads to perform certain actions, in particular the action to send a resource P through the barrier and to receive a resource P from the barrier. The first 4 triple, the one for the allocation, makes sure that the send and receive assertion that the P in there, that it's the same for both sending and receiving. So you pick which P is sent through the barrier at the time you allocate the barrier, and therefore we know you can't have any mismatches. And then because there's a separating conjunction between the two, you can hand them to different threads. And the next 4 triple tells us that if we have the exclusive right to send P through the barrier, and if we also have P, then we can call the signal function, and it will consume these 2 arguments. So the maybe slightly funny postcondition true here means that the ownership we put into the function is gone. As far as we are concerned, we're not getting anything back from the function. Wait is the final 4 triple here on the list, and it consumes the capability to receive. And when it returns, we know that it got the P from the barrier, so it can hand the P through the postcondition to the enclosing program. Now, this covers the case with one waiter, but of course we would like to cover multiple waiters. And if we look at the ownership transfer that we would have with multiple waiters, where we would have the worker thread kind of sending something to all of the other threads. So in this case, maybe they send P to the left and R to the right. And because the two waiting threads go on concurrently, computing on the P and the R, we have to make sure that we actually have that P and R describe disjoint pieces of the state. So the worker thread will have to have P star R before triggering the barrier. Now, the way we express this in our specification is by adding a fourth rule. Namely, we allow clients to split the receive predicate. So if we have, the capability. So if we have the capability to receive P star Q, disjoint pieces of the state described by P and Q, from the barrier, then we are allowed to split this into two capabilities so that two threads can concurrently wait on the barrier, and one thread will get P, and the other thread will get Q. So turns out that's all we need to verify clients using the barrier. Now this spec is not new and it's not ours. It has been proposed first back in 2011. The original proof of correctness of the specification was flawed and it was subsequently fixed by some of the same authors. And the reason I bring this up is that the fix was done by introducing a new logical idea, a new logical tool, which we call named propositions. And this is kind of the key of the proof. So now I'm going to explain what these named propositions are. They are best described by looking at the proof rules that govern them. So the first rule is the one which allocates a named proposition, and well, all it does is it gives a name to a proposition. So we have some P here, and we say that, well, we can pick there will be picked a fresh gamma, and then we will learn that gamma is a name for P. So that's what this arrow here means. Notice that at this point, we are just talking about P, so we don't have to prove P to use this rule. We could very well choose P to be false, and then, well, we gave a name to the assertion false. There's nothing wrong with that. And the second and last rule for named proposition is the one which tells us that there can only be one proposition with a particular name. So if one thread thinks that gamma is a name for P, and another thread thinks that gamma is a name for Q, well, then P and Q must really be the same assertion. Now, these rules are not quite right yet. I'm going to come back to them later and fix them. But the most important question now, of course, is how do we justify the soundness of these rules? I mean, we can come up with whatever we want, but that doesn't mean that it actually makes any sense. So in prior work, this has been done in a rather ad hoc way by going to the model and proving some new proof rules. And what we would like to do is to do this kind of the Iris way. So we would like to derive named propositions from, well, some kind of simple foundations, whatever that could be. And the idea is that this is essentially just a piece of ghost state. So if we look at named proposition with slightly different lenses, we can think of there being a table somewhere in our ghost state which stores all the propositions that we gave names to. And then the first rule will just allocate a new row in that table. It will look for a fresh name, and we'll put the name and the assertion associated with that name into the table. And the second rule will witness the fact that, well, there can only be one row with name gamma. So if the assertion in that row is P, and if it is Q, well, then P and Q must be the same assertion. So this brings us back to the idea of wanting to have ghost state, which talks about logical assertions, because that's what we have in this table, right? So we come back to this problem of higher order ghost state. So I hope this convinces you that there is like some reason to want to have that. So let me briefly demonstrate how we are going to support, how we extended Iris with support for higher order ghost state. So well, we have the cyclic dependency here, and clearly we have some trouble with our ghost state. So maybe we should be calling for some experts with ghost state. Who are we going to call? Well, yeah, you might think it's the Ghostbusters. The problem is they can deal well with first order ghosts, but they don't really know what to do with higher order ghosts. So it turns out we have to ask for another hero, namely Step Indexing Man. So he and his superpower to like count and solve cycles is equipped to handle higher order ghosts. Step indexing is a technique that has been developed back in 2001 by Appel and McAllister, and it's commonly used to solve recursive occurrences that occur in modeling higher order state. And it's actually also already been used in Iris to model a similar recurrence occurring with invariants. So what we did to have higher order ghost state is we kind of equipped the PCMs that make up the ghost state with a step indexing structure. So essentially, we come up with a new algebra class, which we dubbed Chimera, which has a bunch of rules governing it. And the idea is that chimeras are, well, they are PCMs, so they have a composition operation, which has to be associative and commutative and everything. And they also have the structure you need to do the counting for the step indexing. And furthermore, and that's a tricky bit, chimeras make sure that these two structures, that they interact nicely. So as you go on counting, you shouldn't be losing the way that you can separate the resources over the different threads. And as you compose the resources, you shouldn't screw up the way that you're doing the counting. Next, we need to provide a way for the user to properly express the dependency of their ghost state on the Iris logical assertions. Because assertions don't exist yet when the user defines the ghost state, so we can't just let them pick a fixed chimera. Instead, we let them pick a functor so that they can properly factor in the dependency of the ghost state on the concrete structure of assertions. And finally, we essentially tie the knot by taking a fixed point of pretty much this functor. And then, well, by following these rules, it turns out that we can now rely on a step indexing man to make sure that we're actually safe in this cyclic world. So then we get all the nice behaviors that we want, and we don't run into any troubles with endless cycles. Now, unfortunately, it turns out that using step indexing to solve this problem is not without cost, as you would expect for any superpower. So we have to slightly change the rules for named propositions. Namely, we have to add this little triangle in the second rule. So what we have here says that if gamma is a name for P and gamma is a name for Q, then we know later that P and Q are the same assertion. We know it at the next step index. This is not entirely surprising either. The same later already appeared in Iris with invariants, because we also use step indexing to make sure that invariants work out nicely. And furthermore, it turns out it's kind of necessary in the sense that if we remove the later here, or if we remove later for invariants, as we discovered in recent work, then we can actually derive faults in our logic. So we have to do something about that, and what we did is with the step indexing, we get this later modality. All right, so the good news is that this later doesn't actually leak. So this is the real specification for the barrier. It's just what I showed earlier. So the user of the barrier doesn't have to be concerned with the fact that we are using higher order ghost state somewhere inside this proof. Laters don't appear in the specification. So to wrap up this second half of the talk, we extended Iris with a possibility to do higher order ghost state, and we sticked with this idea of resting Iris on simple foundations. So the only thing that changed is that the ghost state is now not a PCM, but a chimera. There's some step indices appearing in one of the rules, but it's still not all that complicated. And the good news is that if you don't care about the step indexing stuff, if you don't need higher order ghost state, you don't have to care about chimeras or anything like that at all, because PCMs trivially lift to chimeras. So in this talk, I gave you an idea how we encoded named propositions using higher order ghost state, which is like a more general concept. In the paper, we also introduced some other forms of higher order ghost state, which could not be handled in prior work, including like more than second order ghost state. And we show how we can handle that in Iris. And furthermore, we show that we can actually use ghost state mechanisms, different ghost state mechanisms, and compose them to more interesting compositional structures, even with higher order ghost state, which again was not possible with prior work. We also show how in transitioning our model from PCMs to chimera, we could actually simplify the definitions of most of the logical connectives in our model. And finally, we have a brand new Coq formalization, where we don't just verify the soundness of the logic itself, but also the examples which we have in the paper are verified in the logic in Coq, which in the prior Coq verification was just not possible due to performance reasons. In recent and ongoing and future work, we are trying, we are encoding invariants also using higher order ghost state. So we are actually able to further simplify those core foundations that make up Iris. And we are using named propositions, we are applying it in our verification of Rust. So with this, I thank you very much for your attention.
Any questions?
Max New, Northeastern University. So partial commuted monoids are monoids in a category of relations, and Lars and them have done this stuff with the step indexing in this step index category, topos of trees. So do these cameras have a nice characterization similar to that, but like in this category of step index things? Or do you know? I'm just...
Yes, so, I mean, Lars's approach essentially can be, you don't have to go full topos of trees. You can, like they call it COFIs, and then you don't have to go all the way to the topos of trees. And chimeras are an extension of COFIs. Essentially, they merge the COFI axioms and the PCM axioms and make sure that they work together properly.
Thank you.
No more questions?
I have a small silly question. You send, you split the receive, but I assume you also split the send. I was confused by that part.
Sorry?
When you make
No, you can't split the send. That wouldn't make much sense. I mean, the moment you call signal for the first time, all the waiters are dropped, are triggered, and go on. So all the assertion that everything that's ever transmitted through the barrier has to be provided the very first time you call signal. You could call signal again, it would be idempotent. It wouldn't do anything because the barrier has already been triggered.
Thank you.
Okay, let's thank the speaker again. There's a short break now.